Hello, welcome to lab number 10, the last lab in 1500. Um, last lab is a good time for me to say thank you for bearing with us. This is not the normal way we like to do labs, but what can we do? So make sure you submit your work on time so it can be graded as we come to the end of the semester. All the best, my friends. Conductivity today, conductivity in aqueous solutions. You certainly have talked about strong electrolytes, weak electrolytes, non-electrolytes. The strength in that case has to do with the propensity to create ions in solution. So you take sodium chloride, we know it dissolves. What happens? You have the sodium ion surrounded by water molecules, the chloride surrounded by water molecules. These two are independently moving in solution. That's what we mean when we say aqueous. So we'll be looking at aqueous solutions. Strong electrolytes create ions on a one-to-one basis. Weak electrolytes, not so much. Example of a weak electrolyte that's discussed in the lab manual is acetic acid. That is, acetic acid just partially ionizes. And so if you start with 1 mole, you might only create 0.05 moles of actual ions, with the rest of the species remaining where it was. All right, so conductivity in this case, with a data logger here, connected to a chemistry sensor and connected to a conductivity sensor. The way the conductivity sensor is, the sensing electrodes are inside there, and this hole is to wash out, clean out whatever was there before. And so there are 3 scales here, 0 to 1,000, 0 to 10,000, and 0 to 100,000 microsiemens per centimeter, that being the unit for conductivity. So let me start with distilled water. Our distilled water goes 2930 microsiemens per centimeter. The lower number is the pressure, and I can't exclude it at the present time. So that's our distilled water. Has some conductivity for sure. Now let's look at the ones you asked to profile. We look at the effect of concentration for HCl, 0.05 molar, 0.10 molar, and we do the same for acetic acid. Let's start with acetic acid. So the way you do it is, and this was distilled water, but I'll all the same wash it. Kind of get rid of the excess by shaking it a little. And then when you put it in, you gotta go like that, just to make sure that an air bubble is not sitting in between the electrodes. So 0.05 molar acetic acid, the value is 398 microsiemens per centimeter. All right? In this case, I'm going from a more dilute solution to a more concentrated. So in this case, I really don't need to rinse, since it's the same substance. All right, acetic acid, 0.10 molar, 535 microsiemens per centimeter, 535. All right, now let's go to HCl. Hydrochloric acid. In this case, certainly I'll take the time to rinse through the hole there. And then I'm going to go into 0.05 molar HCl. Let's see what that looks like. What you can see here is that it's flooded. It's showing a round number like that. It means it's flooded. I'll go to a length sensitive scale. And it still says I'm 10,000, so it's still flooded. So let me go to an even higher scale. So look at that. In this case, let's read it as 19,940 microsiemens per centimeter, 4.05 molar HCl. Let's get into now twice the concentration, 0.10 molar. What a big number. 34,788. Let's read it that way. So that's the conductivity for 0.1 molar HCl. All right, moving on. So hopefully you're completing the tables or jotting these numbers down. I'll certainly give it a good rinse this time. All right, who is next? Let's try 0.10 molar sodium chloride. There we go. Let's go 16,080. 16,080. Sodium chloride. All right, moving on to 0.10 molar HCl, kind of doing it again here. Again, a big number, 34,350, kind of jumping around, but that's the nature of measurements. So you sort of kind of read in the middle, 34, let's go 340. All right, moving along. Ammonia. 0.10 NH3 ammonia aqueous. Much lower value. I'll go to less sensitive scale. 376 microsiemens per centimeter for ammonia. Way above the baseline. The baseline is for water, 30 microsiemens per centimeter. Phosphoric acid, 0.10 molar phosphoric acid, H3PO4. Floods, go back to a more sensitive scale. Less sensitive, rather. So there we go for phosphoric acid. Let's read that as 10,915. Phosphoric acid. Sugar, 0.10 molar sugar solution. Let's read that as 182 microsiemens per centimeter. All right, done with the sugar. Calcium chloride, 0.10 molar calcium chloride, CaCl2. Let's go 16,770. A few more measurements. Sodium perchlorate, NaClO4, sodium perchlorate, 0.001 molar. So we're looking in this case at the effect of charge. These are +1, -1. Let's read that as 415. 415. Now we'll go to magnesium sulfate. +2, -2. Let's read that as 860. 860. 3 more measurements. How about Pepsi Cola? Haha. Let's read that as 1425. Pepsi Cola. About Pepsi Cola. Ingredients: carbonated water, high fructose, caramel, phosphoric acid, caffeine, citric acid, natural flavor. All right, just 2 more measurements. Let's look at the effect of temperature. 0.1 molar sodium chloride, 0.1 molar sodium chloride. There's an ice bath around here. Let's remind ourselves what 0.1 molar sodium chloride looks like conductivity-wise. We've actually seen it already. Let's read that as 10,520. And then we'll put that in a nice bath. All right, let's read that as 9230, 9230. And I think that concludes the measurements we were supposed to make. So let's review. We looked at the effect of concentration. We looked at two substances, HCl and acetic acid, 0.05 molar, 0.1 molar, 0.05 molar, 0.10 molar. Done with that. Then the other thing we looked at, apart from measuring the conductivity for a number of substances, we did look at the effect of charge. Sodium perchlorate, magnesium sulfate. And then, in the end here, we looked at the effect of temperature. How does temperature affect conductivity? We can assume in this case that the temperature was, can actually measure it. Doesn't like that one. All right, wasn't fitting in properly. So that's the conductivity up there, and the temperature as measured is 2.6 degrees centigrade. The other temperature you can assume it was 18 degrees centigrade. All right, my friends, that concludes the measurements for lab number 10, our last lab. Happy Thanksgiving.